recording started here. Good morning, everybody. Good morning, you. It's like so cold. At least there's two of us, right? So there's one student here, and it's certainly because of the cold. No apologies from anyone required there, but I see there's a number of you out there, which is good. So for those of you on the recording, I know the video is a little different. The video experience is going to be different for you, but we have Stephanie Huffman here from TuTh Houston, and she's going to talk about one of the best opportunities I've ever heard for people that are about to graduate and those who are thinking about it in another year or so. So I'm going to let her introduce a program. We have a huge grant at the University of Houston, and they want computer science students involved. So Stephanie, please say hello to people.
Okay. Hi, everybody. And I'm going to talk to you and then everyone else too. So basically, TuTh Houston was created to fill the need that's in HISD for the shortage of qualified science and math computer science teachers. Basically because most teachers out there in HISD right now are getting an overnight certification. So they basically have English or history degrees, and they are getting overnight certified so that they can teach science and math to our students. So they created TuTh Houston, and so basically it's a course load that you add on to your current schedule, and we have streamlined plans so it doesn't add any years to your degree, and you graduate with your science, math, computer science degree, and also a certificate to teach. And you will be certified to teach 7 through 12 grades, so secondary education. Basically, what got me in the program is scholarships. I was in class, and they came in talking about it and talked about scholarships. So 80% of the students in the program right now are on scholarship, and TuTh Houston is actually the largest undergraduate funding at University of Houston. So we give out the most scholarships, and right now they're paying for my school, which is incredible because I'm not a millionaire and I need money, and I'm sure everybody else does because I don't think I've ever met a college student that was a millionaire. So we have just been given a specific grant for computer science. So they are in the fall, I believe they're starting a scholarship that's specifically for computer science majors, which is great for you guys. Also, we have a post-bac. So if you're getting ready to graduate, you go out in the industry, maybe you decide, hey, maybe I should try teaching, or even if you're going to graduate and you decide, hey, well, maybe this would be a good opportunity. They're doing, in the fall, for the next year, basically you can take all the classes in the fall, and in the spring you do your student teaching semester, and then come the end of next year you are certified teacher, and you don't have to, well, it hasn't been confirmed yet, but more than likely you don't have to commit to any time with teaching and the whole year next year, so they're actually doing that 100% funded, so you can take all the classes and get certified and everything for free. So that's a really huge deal. And teaching is so awesome because you're building the future generation. You know what I mean? So people think of teachers and they're like, oh, you know, go and teach kids all day long. You know what I mean? But really, it's a great thing. You know, you're building the future. It's really fun. The classes are really, really fun. I had no idea how awesome it would be. The first class, if you want to get started, you sign up and you meet once a week, and they give you the lesson plans. You go out and you teach elementary first, so they don't just throw you right out to high school students. You start at elementary level, then you go to middle school, then you go to high school. And you're teamed up with someone the whole time. And you're teamed up with somebody the whole time, so it's not like you're on your own anyways. It's great for just learning skills, and even if you want to go on to graduate school or professional school, it looks really good on an application that you have teaching experience and that you have this. So I think it's the best capstone that you can have. It does fulfill your capstone. I don't know if I mentioned that already, but because you're going to need a minor, double major, or a capstone to graduate, so it does fulfill your capstone. And what better to fulfill that and get scholarships in the process. So it's great. They also have paid internships. So I did one this past summer, and we taught students during the summer. They came up with their own inventions. We did robotics with them, programming, the Arduino, I think. Is that right? How you say it, right? Yeah. Okay. Yeah. And so it was great.
You learned 3D printers?
3D printing, yeah.
Kids went on to the Inventors
Yes,
Association.
in May they're going to go on to the it's like the Young Inventors of Houston big thing that they have going on. So yeah, it was a really neat experience for these kids to learn. They're in 6th, 7th, 8th grade learning about the engineering design cycle, which is incredible. I learned about it too, which was even cooler, you know. So all of our graduates, they graduate with job offers, so 100% job guarantee, and the starting pay for teachers, especially if you're already, if you actually have a degree in what you're teaching, is like $55,000. So that's pretty good, and that's for a 9-month contract. So you have the summers off. You can do computer science in the summers, or you know, and even teach and do little projects on the side, you know. So it's a great opportunity, and I think I covered everything that I wanted to cover. Thank you so much.
I'll toss a couple of things off also to talk about. So I fill out lots of references for students going to graduate school and going to research programs. One of the questions on the Common Grad School app is, how good is this person at teaching? How would you rate their ability to teach others? So you can just put a big old checkbox next to that if you've gotten certified to teach. I have found in my career I have never understand anything as well as I do when I have to explain it to someone else. And let me tell you, if you don't know your stuff, kids know. You guys are ruthless. You'll call me out on stuff, right? And that's one of the things I like the most about teaching. I really get to dig in, and I really have to challenge myself that I know, you know, what I'm talking about, which is great. Another thing, financially, being the oldest person in the room and on this WebEx right now, there's very few pensions left in society. They've all got blown up in the early to mid 1980s. You know, the old days of where you would work for someone for 20, 30 years, and then they would pay for your retirement and health care. Those defined benefit plans have vanished for all but a very few careers. Law enforcement, military service, the postal service, and teachers are on that list. So you can work for 20 years in Texas and qualify for a pension and benefits for the rest of your life. You can move to Mexico and get that check deposited in your bank account every month. What a lot of people do is they go on and then start a career. I mean, you're going to be 40 years old for some of these guys that come out of the Air Force and things, and they go into teaching. And I'll warn you, if you want to do something like this, there's a really big chance you're going to fall in love with teaching. It's a lot of fun. So unless you just suck at it, which I can't imagine you guys doing that, they're going to snap you up, especially if you're younger. They're going to see lots of commonalities with you, and you're going to be the cool person in the room, like right off the bat. So it's a huge, I mean, I would have killed to have had an opportunity like this. There's millions of dollars in scholarships at stake here. So basically, you graduate, you can do this for a year, you end up with a teaching certification, and that's a job you can take to any place on the planet, certainly any place in the United States, walk in the door. It's not like, we don't have factories in the U.S. anymore, or that opportunity is not available in this state. That's really in the states that grow apples. And, you're not going to have any of that problem. Every place needs teachers. So it's a great insurance policy for a career as well. If you just get sick of your job and want to walk away from it at some point, you can teach and have a lot of fun doing that and make the world a better place. So, I'm tempted, I got to tell you.
We got to get you to classrooms with that.
I'm tempted to come and I wonder, is it too late to start over? Yeah, it's probably, right? So, but I've been teaching on the side for 18 years for U of H and just became a professor finally after retiring last year. So, yeah. I'm happy to talk to you guys more if you want, and we have some material. I'll send you guys an email about it, but I'll put it on the drive for us as well as it comes in. And they
teach Houston too. I don't know if I
teach. Yeah, you did, and I did too. So there's an information session coming up soon that we need to let you know about in a couple of weeks, right?
Next week, I believe.
Next week. Okay, so get me that stuff soon.
Yes, we will.
And you remember I'm Kevin Long.
Yes.
Okay, so send that to me, and I'll get that out to you guys. Thank you very much for coming. So it's fun to start off with something a little different, isn't it? Especially something that's so positive. So I'll tell you guys, computer scientists, it was a dirty word to be a nerd when I was your age, and people used to tease, and I held my head up high. I'm not quite sure how I did it, but I managed to do it, and you know, we've absolutely taken over the world. So it's awesome the way this has worked out. My plan is working perfectly, as I tell people. That's one of my lines, and my other line is, I plan to live forever. So far, so good. I stole that from Stephen Wright. Okay, so last time we had finished talking about most of the stuff that goes on in hardware-wise inside the router. We took a look at the switch and the line cards and things that are going on there, and we began to take a peek into software-defined networking. There's just a little bit left that we have to do for Chapter 4. We talked about fragmentation, and we talked about a ton of stuff. Network address translation, V4 addressing. We talked about some subnetting a little bit, and we took a peek at these slides. So we're going to wrap this up quickly and then move right on into Chapter 5, because again, the reason why the 7th edition of this textbook exists is because they split what was the one chapter on the network layer into two pieces. The network layer is the layer where you have IP software, and that's what distinguishes routers from other pieces of equipment. So routers run layer 3 software, things below it do not, things above it are hosts. So most of the devices that your equipment, that your packets travel through, the equipment and the internet are routers. That's what, as computer scientists, we're most concerned with. So we'll quickly roll into sort of what's going on. All right, so to get on back to SDN again, the idea is that for 40 years, we've built these basically data centers, but they're spread out all over the planet, one computer at a time. They all work together. We call it the internet. They're all Intel-based servers for the most part. They're running Linux, Unix. They run software that inspects their state in life and their position on the network and decides on where to send packets. The result of running that software is always a forwarding table. Some people will call it a routing table. I'll try to stick to forwarding table because it's a more general term that we are trying once again to use. So the forwarding table has to be produced by this software, and it has to be given to the line cards on the switch fabric of your router, the things that are receiving these incoming bit streams, so that they know what to do with them. Do I drop it? Do I delay it? Do I send it to this port or that port? Those decisions are made entirely based on the contents of this forwarding table that you build. So there's two things that are going on in the router. And what we are going to change this terminology to for a few minutes is the terminology that will be used as more and more people adopt this different way of approaching this problem. And the different way of doing it is going to split the two pieces apart. You will leave the line cards that are receiving these flows of bits sitting where they are, because that's where the bits are. You've got to solve the problem there. It's sort of like you can't move the intersection someplace else just because you move the control signals that are controlling the stoplights to a data center. I mean, the cars are still where they were. Right? So you still have to deal with the forwarding there. And what you'll do is take the software that's building those forwarding tables, the routing software, and remove it from the router and centralize it in a data center. So this concept is called software-defined networking, because basically you're going to be running programs now that we will write that run inside a big data center, AWS or Google or wherever it might be, maybe a provider's own data center, like AT&T is a big network, maybe they run it in their own. And inside that center, you are going to be able to make some huge innovations that we've struggled to make for 40 years, specifically because these servers are spread out inside of every router, and you're limited in their capacity. I mean, nothing can compete with the size of servers that you have available to you in a cloud-scale data center. You could never reproduce that work inside a single router. And it's really very difficult to imagine how you would harness the power of 1,000 routers and orchestrate getting processes completed the same way you would if they were all sitting together, the same make, the same model, the same software, same exact version of OS, et cetera, that you can pull off inside of a data center. So we beat our heads against the wall forever for this stuff. And couched behind all of this is sort of the most fundamental problem of all with routing, which is it was developed in an era when people had to contribute money to this new idea of networking. And so you had to take some money that you would have used. Pardon me, I've got to keep from choking here. I just will show you it is a Diet Coke, or it's a very cleverly disguised can that looks like a Diet Coke. We're really now. Okay, so that's my story though. So you can have some money that you'll pitch into this project, and basically it goes all the way back to the very beginning days of ARPANET, where we didn't want to waste very much money. We didn't want to invest very much money in equipment that we weren't going to be controlling. And this was going to be money that would be spent on devices initially called IMPs that we would call routers today. They're going to handle everybody's traffic. So, you know, why do you want to give away a bunch of your money to something that you're not going to have control over? You are going to have to agree with everyone else on how it's going to be operated and run. So we kind of took a bare bones approach, and we agreed on some minimal things that routers would do and the way the software would work. And it led to the design of TCP IP and the software layers that we have in there as well. But one of the restrictions that we made for ourselves is, you know, we're only going to worry about where a packet is trying to get delivered. We do not feel we have enough processing power. Can you imagine 40 years ago the size of processing that we had available to us? We didn't have much time to do things, and so this was a time when every packet as it would come into a router would actually be handed to the operating system, which is totally laughable now, and I'll explain how different it's become. But you'll take a packet and you'll hand it to the OS, and this routing software would look at the destination address, the IP address that you're trying to reach, would look in a table that it had built, the forwarding table, and it would see which port it thought was the best to deliver this packet to continue it on its journey. And you didn't have time to look at anything else, like where it was coming from. It really doesn't matter. The only thing that really mattered is where it was going to. And you know, if you get to an intersection in the road and you're trying to reach I-10, why would it matter where you were coming from? If you're going to I-10, everybody goes the same way to get to I-10. You take this exit on the right-hand side of 45, for example. So that's kind of the approach that we took. The problem with that is as things became bigger in scale and more complicated and sophisticated, particularly with some of the negative things that happened, we wished we had built this to take a look at more things than just where you're going. Like, who are you again? We can't even really ask that. So we built other devices to kind of enhance what routing does, and certainly inside of organizations, universities and businesses and things like that, we run all kinds of other protocols inside of our routers. They're all capable of it. I mean, after all, it's an Intel-based Unix server. You can run anything on it. And so inside of routers and the internet, we run NAT and DNS and firewalls and all kinds of packet filtering and load balancing and, you know, kind of monitoring and telemetry, and we run other types of non-IP protocols as well. We put line cards in that assign telephone numbers to people as well as IP addresses and all kinds of things like that. But on the internet, we don't do any of that stuff. It's just basically destination-based forwarding. So trying to break from that 40-year-old habit and become more intelligent and sophisticated to write better software is another opportunity that's been, you know, this is the golden moment to take advantage of this, and for the first time in maybe 40 years. It's certainly the best one is while this is going on. So you'll see us throwing lots more at SDN than just simply taking the routing responsibility away from the table. So you can't stop talking to the router. So if you take this software away, you're still going to have to build forwarding tables. And in order to build good forwarding tables, you need to know everything you can about the network. What ports are up and running? What's the bandwidth of each of them? How are your buffers doing? Are you dropping very many packets? What types of addresses are you seeing coming in from these other routers? What networks are they coming from? Because I could presume that I should be able to send a packet back in that direction and reach that same place that I just received something from. So those types of telemetry and statistics information are really important. So we're going to replace the routing software with something that's much, much simpler and much more compact, and it's going to maintain a connection to this data center wherever you're going to run SDN. and it will provide all of those types of updates. Hey, this port went down. Hey, I can see this network. Hey, I'm congested. I see new packets coming from new network numbers I've not seen before, et cetera, et cetera, et cetera. Right, so you'll control the router remotely, reboot it, load new software, install new routing forwarding tables, but you'll also have to have some sort of an API that you use to keep in communication with this. So basically the idea is in this STN model, you'll push down these forwarding tables, and we're going to genericize the name of those a little more to consider them to be flow tables, because we're going to start looking at more things than just the destination address. So OpenFlow is one standard, if you will, that people have adopted that installs this API in a router, gives you a way to talk back and forth. It gives you basic mechanisms, and it's easy for a router vendor to adapt OpenFlow to their hardware. So once you do so, then your hardware looks like everybody else's hardware in the way that you ask it something or tell it something. Like no matter who makes the router, if you're running OpenFlow and you want to know how many ports do you have and what do they connect to, the message is the same, regardless of the manufacturer and the vendor. So we can start seeing new entrants come in and building lower cost devices, more competition among it. Just to recap something I'd said three lectures ago, I hope, this business is still like the mainframe business was when I was a student in college. You would buy a mainframe from, say, IBM. They were King Kong at the time. There were others. And you bought everything from them. You bought all of the terminals that you use to attach to the mainframe, the network that attached these terminals, these dumb PCs, to the mainframe. That was all equipment sold by IBM. The protocol that it ran, Token Ring, was developed by IBM. If you needed parts or cards or cables, those things all came from IBM. If you wanted to write a program to run on this mainframe, you wrote it in the language that IBM developed, and you went to IBM school to learn how to do it. If you needed help, you hired IBM employee programmers to assist you with stuff. And all the peripherals you needed, printers and hard drives and keyboards and all of that stuff was all IBM. From top to bottom, you bought it from one vendor. There were a lot of issues around that forced them to kind of open things up, antitrust law specifically. IBM got very close to being found to be a monopoly at one point, and so they licensed off the ability for other people to write software, and that was successful, and for a bunch of reasons. It was successful at avoiding antitrust law and getting broken up like AT&T was, but it was also successful because it increased the rate of innovation. So now think about how you buy a laptop. You don't do any of this stuff. You buy a laptop from whomever you want. You pick whatever operating system you want to load on it from another vendor. You buy software programs from as many third parties as you like, or you can write your own. You don't have to go to the laptop vendor's programming school to learn how to use it because it's all been basically standardized. You can pick whatever language you want. And peripherals, well, you pick whatever hard drive, thumb drive, those standards are all open. You can develop your own devices if you want, plug it into the USB port. So that's where we want routing to go. Right? So it's not there yet. SDN is moving us in that direction. So that's kind of what happens. So the idea is we'll genericize this concept of the instructions that we give a router, which again right now are simply, where are you trying to go? Turn left. You're trying to go here? Turn right. Just destination-based forwarding. So what this flow will do in a standard like OpenFlow, with their terminology, they basically define patterns. So what I just talked about was a pattern, right? Are you going to this address? I'm going to look to see if I can match the address you're trying to go to with an entry in my forwarding table. And if I do, if I see that you match the pattern of something I've got, then it's a match, and I will take what action I can. Well, in the case of a traditional router, there's only one action you ever take, which is send it out on the port number specified. But that's an example of pattern matching. So we're going to let you match other things besides that. We'll let you take actions like forward the packet, but we'll also let you do other things as well, like change what's in the packet, change the IP address. Why would you ever want to do that? Well, NAT. We talked about that last time. That's an example of where you need to have the IP address changed. Maybe you change the port number. Maybe you drop the packet. Maybe you send it a different way than other people. You'll come up with some prioritization, which we struggle to do, and with counters to kind of let the algorithms up above know what's going on. So here's an example of what some of these things might look like. If you're coming from here and you're going to here, then drop it. Otherwise, if you're going to here and you're coming from any place else, then forward it over port 2. Also, if you're coming from this specific IP address, regardless of where you're going, send that packet up to the controller, because that IP address is for a port on a router that's sending out alarms or something like that. Make up some reasons. So a little better diagram is this one. And the main thing I want you guys to pay attention to at the bottom of this is there's a list of some of the other things that we could be basing our decisions on. So if somebody asked you how to get to a destination, there are times when you want to know more than that information. Well, how long do you have to get there? Well, do you want to travel on highways, or do you want to take the scenic route? How much gas do you have left in your tank? Because one of them has a gas station pretty soon and the other one doesn't. Are you leaving now? Because if you're leaving now, I'm going to give you different directions, because we're getting into rush hour, than if you're leaving later this evening. Even Google Maps will ask you some of these questions when you ask for maps. They'll ask you, when are you planning to leave? Are you going to take public transportation, etc. So here are a bunch of fields that arrive in every single packet for the most part. Routers have access to some of this at layer 3, some of this they have access to it at layer 2. But one of the things that I might base my decision on is on which switch port did you arrive? Maybe there's a reason why I want to know that. If you're in a virtual LAN, which we've talked about before, this is a way of letting someone still believe that they're part of a local area network even when they are elsewhere on campus, by programming the devices at the switch level at layer 2 to behave in exactly the same way, to mimic your behavior. So when you open your printer list, for example, you don't see the printers that are actually around you on the LAN, because you're plugged into a switch port and the switch port's been told to create the illusion that you're back in the chemistry department. When you open your printer dialog, you will generate packets that will be forwarded by these switches back over to chemistry without you having to do anything like a broadcast differently. And any packets that the printers are sending out to announce their existence over there, you will see, because the switches have been programmed to create that illusion for you. Very, very powerful concept called a virtual LAN or a VLAN. We talked about that before, but I may want to route your traffic differently based on what virtual LAN you belong to. If you're being asked to be routed to the badge printer on campus over at the police department, or over at the Cougar, whatever that welcome center is near the Hilton Hotel, I may not let you send packets unless you're on the VLAN with the HR department. And there may be HR people planted in various places around campus, but only their packets are going to be allowed to be on that virtual LAN. I could look at your hardware source and destination address, the type of Ethernet you're running, move up a layer. I could look at your source IP address, your destination IP address, the protocol that you're running at IP, and also the protocols that you're running at layer 4, UDP, TCP. Are you running a flow control protocol? Is stream control protocol? Is this ARP packet? Is it an IP packet? Is it a routing packet? The only one of these we look at right now is this one right here, just the destination IP address. So you can, it turns out, do some very easy to understand, clever things with this model. So for example, if all I want to do is teach this now SDN OpenFlow capable switch, it's not a router, just a router anymore. If I just want to teach this new device that I've replaced my router with that speaks OpenFlow and it's, you know, hella fast at forwarding, if I wanted to do routing, I can still give it rules that look like old-fashioned routing table entries, forwarding table entries. I don't care what any of the other values are except the destination IP address. It's back to a router. And the action I tell you to take is forward it over port 6 in this case, as an example. But if I would like to now take advantage of this pattern matching to build some other devices that you've heard of before, like a firewall, for example, I can say basically, if you're trying to get to this port, drop the packet. Or if you are coming from this IP address, drop the packet. Or if you are sending things from this hardware address, duplicate the packet. Send one copy to Wireshark, and I'm plugged in over here on this port, and send another copy to a fake server that we've set up with something that we call in security a honeypot to make you think that you're really talking to your target when in fact you're talking to something that's basically can be torn apart and will harm nothing by doing so, but will waste your time doing it while we figure out sort of how to tell your packets apart from everybody else's. So this is something you would do to mitigate a denial of service attack, for example. Another example, if you want to just have this device behave like a switch. If I know what source MAC address you're coming from, maybe that's how I tell what VLAN you're on. And so instead of having to go out and program all the VLAN stuff on all of these switches, we have these new, more generic devices. They can do routing, they can do switching, they can do firewalls, they can do load balancing, they can do all these other kinds of things in every device. So we don't have to worry about, where do I have the nearest router, and now I got to program the switches to get this stuff securely over to the router. There are things that you might have these things do, like encrypt. Maybe you want your packets encrypted if they're coming from a certain site and not worry about whether the host knows how to do it or not. Maybe you want to convert it to IPv6 from IPv4. There's kind of an endless list of things you can do. So some providers have found this so powerful, like I've mentioned a few times. AT&T supposedly has 85+% of their network now being managed in this fashion. So they've gone across all kinds of equipment in their network, and not just internet-based equipment, but all kinds of telephony equipment as well. And they've implemented this standardized API, and no matter who makes it, they can kind of talk to it with the same rules, and that's how they can quickly configure things orders of magnitude faster than they've ever been able to do before. So all of these basically follow the same pattern. You can describe a rule if you can identify the packet streams that you want to perform a specific action on by pattern matching with those fields that I gave you, then you're golden. You can do whatever you want. So super powerful. So here's an example, and I've got something going on with the cable, so hold on just here a second. I got my cable's stuck under the monitor. Okay, sorry about that. The way you'll implement this is by having something that runs this OpenFlow software. You'll interact with this controller, and then it in turn will push these rules out to these various devices. So in this example, I show a server, and maybe it'll be a server, maybe it'll be just a virtual machine running in a data center somewhere. But what it's done is it's pushed rules out to 3 routers just to kind of give you an idea of what they look like. Oops, it's kind of hard to do it if I don't let you look. The first one says anything coming from IP addresses that start with 10.3 going to 10.2, send it out on port 3. So now you've got packets that are headed towards 10.2 going out across this link. Then the next router will have a different set of rules. If it's coming in port 1 from 10.3 and it's trying to get to 10.2, send it out port 4. So it's going to come through here and just make a turn and go this way. And then finally, when it gets to this router, if it's coming in port 2 and you're trying to get to 10.2.0.3, it's over here on this port. 10.2.0.4 is over here on this port. And presumably there's an otherwise if it's trying to get to other addresses in 10.2s, then do this with it instead. So these look like routing table entries. These are easy for you to understand. You could easily, hopefully what's going through your head right now is, that's it? Yeah, that's it, right? So you just have some rules that you're putting through here. Okay, so how do these tables get computed? Where does this get generated? That's what used to happen inside of every router, but it's the reason why we now have a next chapter. So we're going to dive right into that. You notice there's not even like a welcome to chapter 5. It just kind of moves into the next slide. So what we're going to look in this one is some SDN controllers and then some other control plane things that have been around for a while, like network management and ICMP. And we'll also look at some traditional routing algorithms. So there's an acronym soup at the bottom. I'll walk you through a couple of these. We'll talk about some of them more. The dominant routing algorithm, the program that you run inside of your routers to calculate your forwarding tables inside of an institution, is almost always OSPF, Open Shortest Path First. It was proprietary to Cisco for 20+ years. They sold a lot of routers because that's the only way you could get OSPF. you had to buy their router because it would only run there. It's now in the public domain. They gave it away 2.5 years ago. Why? Why would you do that? Why would you give something away? Because they see that as the future as well. They feel like the hardware business will diminish for them, maybe vanish over time, and what you're going to be buying from them are subscriptions for enhanced versions and support for routing algorithms and calculating new tables and keeping network security rules up to date, live, and things like that. BGP, Border Gateway Protocol, is the protocol that runs on the internet. So if you have a router that connects your network to the internet, it's got to run typically 2 protocols. Very often OSPF to talk to the routers inside of U of H, and then BGP to talk to the routers out on the internet. So you'll have these dual-brained things at the edge. OpenFlow, we just talked about. ODL and Open Daylight and Open Network Operating System are other instantiations of these types of theories or these types of approaches. ONOS is used by carriers because for the last 100 years, network operating systems, NOSes, those are things that they would run to control their equipment, the telephone company equipment, for example. And then ICMP and SNMP we'll look at a little bit later. Okay, so again, to recap, there's 2 things going on inside the network layer, inside of a router. You've got to actually decide where you want things to go. That's routing. And, you know, I've done it this way for years and years with this slide. And today is the last time, except it's actually not going to let me edit the slide. Really? Are you kidding me? Cut? What is it like protected or something? Wow. My keyboard's not working? Okay, so I want to save this out. I don't know why it never occurred to me to switch these. I gripe about it every time. Routing should come first. First, you're going to decide where you want things to go. If you're going to take a big, giant vacation around the world, the first thing you're going to decide is, where am I going to go? And talk to a travel agent to figure out, all right, how am I going to get to the airport? Is your sister-in-law going to drop you off? Are you going to take Uber? You're going to stab yourself in the foot rather than take a ride from your sister-in-law. You know, like, what are your rules there? Then you get to the airport. What airline are you going to fly? What kind of plane is it? What's your baggage limitation? Are you going to have to ship some stuff ahead of time to get there, maybe to save some money? Are you going to an island? Will you be taking a ferry boat or a bus? All those kinds of decisions have to be made. And then you do it. Right? So then the forwarding actually happens. Then you actually get in the car and on the plane and on the ferry boat. So the routing layer makes the table, makes the rules, and the forwarding is the act of actually moving the bits from an input port to an output port. The way this works now is we have to build these forwarding tables and hand them to every line input card. Every place where there's an antenna or a cable that's bringing data in for you to your router, for you to decide how to forward further. The speed at which this happens is impossibly fast to ever give you a chance to take the packet and walk over to the operating system that's running the routing software, knock on the door and go, hey, I have a packet, here's its address, where would you like me to send it? You do not have time to do that. So we have to do the forwarding decisions inside the line card. So the forwarding table actually gets given to every line card. This would be like giving the soldier all the rules of the field, you know, what you want him to do, or give the farmer all the rules for where to plant the seeds. They do not have time to come back and ask again. So there's 2 approaches to structuring that routing plane: to do it in every router, which is traditional, or to centralize it, which is software-defined networking. All right, so we're repeating ourselves at this point, right? So we've seen this diagram before. We have the routing algorithms that are running. They talk to the other routers. They build forwarding tables, and then that forwarding table is the Bible. That's what all forwarding decisions are based on. So we're going to split these logically. With SDN, we basically just have the routers send information on what is going on that normally they would just hand directly to their routing software, but it's not running there anymore. So we're going to have a control agent, a little CA circle on these diagrams. That's going to be defined by somebody like OpenFlow, for example, and it's the API that you use, the programming interface that you use to exchange messages back and forth. So it's a little bit ironic that you're going to be totally dependent on the network that you're trying to manage to get you the data that you need to decide how to manage it. You know, it's sort of a chicken and egg problem. What happens if the network goes down and you can't get the messages? Well, what happens if the data center becomes unavailable? So you have to take some care with this, and you do have to let these devices have some fallback where they'll just continue running the last table they had for a while until you can get to them again. But if the problem with the router is that all the routes have gone down, then what difference does it make anyway? It's not going to be doing any routing anyhow, right? So as long as you can kind of get messages from it, this will work. This will work well, right? So again, it's the separation. All right. When it comes to writing these protocols, to writing the software that's going to decide what the forwarding table entry should be, it depends on having knowledge of the infrastructure. Physically, which other routers am I touching? Because those are my only candidates to whom I can send packets for their next hop. So I need to know that. But far more important than that, who can they see? Which network numbers have they got the ability to reach? And in how many hops? So presumably, every router can reach every destination on the internet, but some are better choices than others. If I leave here today to go to the airport, I can take any exit anywhere all around campus. They'll all have a way to get me to the airport. Probably a lot of them will converge on the same route shortly. But some are better choices than others based on the fact that I'm in this building and my car is over in the stadium parking lot, right? So that's kind of the idea. So a couple of things that may surprise some people. No router on the internet running BGP has a view of the internet. It's too massive. No one really has that. So you have a decent idea. You know best the things that are near you topologically, not geographically. We're talking about hops. So you may be 1 hop away from Russia and 10 hops away from Rice University. That's possible. So topologically, Russia would be closer to you in that case. So you've got to have a pretty good idea of what's around you and a vague idea of what's beyond that. Inside of an institution, where you may run a different routing protocol like IGRP, EIGRP, RIP, or OSPF, which is the one we talked about a second ago, it's more likely that you will have a comprehensive view of what's inside your organization. It's possible that your organization is so big that you won't even do it there either. For example, U of H has lots of campuses. There's really no reason I can imagine why a router in the computer science department here would need to know about all the details at Clear Lake or in Victoria or U of H downtown. They would need to know how to get things there, and it might still be over an internal U of H network, but I probably don't need to know anything other than how to get to the router at the front of University of Houston Clear Lake. And it'll take it from there because there's probably no better path. No need to know more details. So there's exceptions, but you're more likely to have a comprehensive view of your network inside of your institution. You will never have it outside the institution. So the routing protocols need to build good tables, not perfect tables, but good tables. So what we're trying to do when we move to SDN is to move away from printed maps to Waze, where it's going to nail it every time and knows exactly what's going on every road in the world. And if you plot a journey, it'll tell you exactly now which way to turn that's best. It may be very counterintuitive. You may go like, that's not the way to the freeway. Yeah, but Waze knows something you don't know. It's closed right now. It closed 2 minutes ago, for example. So that's what we're trying to get routing protocols to take a much more comprehensive look. And maybe we'll have a chance to build something closer to a comprehensive map that has more established routing protocols and to get over this destination-based forwarding. So this is a big issue. And I'm going to show you guys another failure of the way we route traffic now that's a direct consequence of doing destination-based forwarding. So we need to have some terminology. So here's a diagram that shows a map of a particular network. It's got 6 routers on it and 10 different links. And these links have costs. So the job of my routing program, which is going to implement some mathematical protocol, like a shortest path protocol or the traveling salesman protocol or some other things that you may have heard of and learned before, is to come up with a decent route. And for most of the examples in the book, and including the online animation I'm going to show you in a minute, we generally start from the router on the left of this diagram, the one labeled U, which makes for some funny double entendres as well, like how are you going to get to V? Well, you know how. Go through U. You have the routing table. Yes, U does have the routing table. So I'll have a little bit of fun, and maybe you'll have a chance to groan a little bit, I hope. If I could ever get all of you to groan once, holding your collective nose, as George Bernard Shaw said, it's the world's best pun. So we have a set of routers, U through Z, and we have a set of links, and the links are described by the pairs that they connect. And these are point-to-point dedicated circuits, so they're never going to connect more than one thing at each end, 2 devices. And this will be helpful for abstracting this. The cost is going to be some measure that either your routing algorithm calculates or that you set for each of these links. So when I ask you, what's the best path to get from U to Z, you need a program that can figure that out. And what determines these numbers that you see on here? Is it the milliseconds of latency based on the distance? Maybe that's the measure that you want. Maybe it's the bandwidth. Maybe it's some measure of that. Maybe it's something that shows you the level of congestion at this very moment at the destination end of this. And there's only one number, but we're coming from U. So maybe the 5 on the top of this diagram is there to indicate that W is kind of busy right now for that path. Maybe it's actually a cost. Maybe these are links that you pay for based on the bandwidth that you consume. If it's a satellite link, for example, you're going to pay by the minute. You don't have a flat rate. And for some of these networks, you may pay a flat rate for your internet service. The providers behind you may not. They may be juggling that all the time. I can guarantee you the phone company has to pay for every packet that you send, in the sense that whatever they bill you, wherever those circuits run, whatever roads they go down, and the cities and the counties that own those roads, they have to pay income tax and sales tax on all the revenue that they're pumping down those cables down that road. So there's usually, when I would do sales calls for AT&T for policymakers, I would call up my tax guy at AT&T and say, how much did we pay in taxes in this city last year that I'm going to go visit? Because we're having trouble. We want their permission to put a cell tower on the convention center, because there's lots of people complaining when they have conventions there that they can't get good cell coverage, and we're wanting to do it, but one of the city councilmen is giving us grief over how ugly they are. Yeah, they're all ugly, and everybody needs them. So, like, what are you going to do? Roads are ugly as well. Gas lines are ugly. Electric lines are ugly. We seem to have all of those. Why are we not putting things in that we need? Right? So don't we have bigger issues? So I would find out how much tax we paid, and then I'd ask a couple of questions. Where are we on the rank of taxpayers? Almost always, we were number 1, meaning we paid more taxes. We were the number 1 source of taxes to that county or to that city. And when you can walk into a meeting and say something like that, that's pretty powerful. It's pretty influential. You can basically lay out, and I would talk to my tax guys and my external affairs guys and go, how much did that new high school they built last year cost? Wow, what do you know? It's the same amount we paid in taxes over the last 2 years. So I can walk in and go, let me make this. You got reelected because of this high school that you agreed to build, right? Do you know that we paid for that high school? If you would have taken all the tax money we gave for the last 2 years that we owed you, that would have paid for your high school. Do you want that to shrink or grow? So it's kind of an interesting business conversation. So that may be a source of cost on a diagram like this, on a cost like this. So the question is, what is the least cost path? As a router manager, sometimes if you want to reboot a router, the first thing you'll do is wean the traffic from it. You will stop sending more packets to it and wait for the existing TCP flows that are there to close. And they usually don't last but a couple of minutes, sometimes a lot less than that. So you'll wean them. And so you'll go into the routes. Let's say you want to reboot W here. You'll go into W and you'll set all the cost into W to infinity. So within a few minutes, everyone will just stop sending traffic to W. It's still up and running. There's nothing wrong with it, but you're getting ready to perform maintenance. So there's reasons why you may want to go in and change those things as well. So some of the decisions that you need to make when choosing an algorithm is how much do you want your program, your routing program, to deal with? Do you want it to have a comprehensive global view of all routers in your organization, a total topology map? Because that's a lot of variables. It's a really big matrix. It's a really long linked list. It's a lot of memory. It's a lot of processing, et cetera, et cetera. It's like Towers of Hanoi with 20 towers instead of 5. Really? Do you want it to be decentralized, where every router performs its own math, or do you want this done in a central location? Do you want this changing rapidly, or do you want these routes to be relatively static? In the internet, you've got some interesting decisions to make, but you do want it to respond to changes in the backbone, because there are links that you don't have any control over, and it's possible things are happening. But inside your own network, maybe on campus, you set it to be relatively frequently updated, because there's lots of people messing with cables and lots of hands in the plant, as we would say. People with maintenance trucks doing other things. They may unplug something accidentally. Powered circuit breakers might get tripped. That's the same one that your router's plugged into. But inside of a data center, you'll probably nail them up static, because it's an extraordinarily controlled environment with backups for power and air conditioning and everything else. And you totally control who's in touching anything. People aren't wandering around trying to run cables and do stuff like that. It's all very carefully controlled. So those routes shouldn't change ever. All right, so a couple of categories of these. Routing protocols can fall into link state or distance vector protocols. The link state ones are the ones that have a comprehensive view of what's going on, and those are going to typically be run with Dijkstra's algorithm. And some of you guys have heard of Dijkstra's algorithm before. So this is one where you'll broadcast out what you can see to everyone else, all the other routers on the network, and they'll all learn what's going on. All nodes have the same basic info of what the connectivity is like and what the costs are like, and they can calculate their own custom forwarding table based on how the costs look from their point of view from where they sit in the network. The routing tables are not the same for every router. They're custom built on a per router basis. That's really important to understand. Okay? So the Dijkstra's algorithm will compute this least cost path, and like all routing tables, it will produce a forwarding table. The purpose of every forwarding algorithm, every routing program on Earth is to produce a forwarding table. That's what they do. That's where the forwarding tables come from. If you don't have a forwarding table, you are not routing. So it's a very fundamental requirement. So we have some costs that we show. We have the distance from a source to a current destination that may be comprised of a variety of costs. If it's directly connected to you, like it's the next hop over, maybe you can observe the cost directly yourself. And then there are ways of sort of building these costs up by accumulating knowledge about the hops along the way. So you have this concept of nodes along the path that you get there. And then we're going to show you how to build one of these forwarding tables in detail. And so we have a set N of routers, and as we go through building our table, one by one, we're going to come to a conclusion that the best path, the lowest cost to get to each one of those routers. And every time we make our decision that, okay, I'm convinced now, I now know the least cost convincingly to get to W, you will move W from the N list to the N prime list. And so that becomes the set of nodes whose least cost path you are confident you now know. All right, so here's what the software looks like. First, it's going to start off by only putting the router for whom you are building this table in the finished list. So N prime is the list of ones that you're done with. And like I mentioned in the diagram a few minutes ago, most of the examples in the book start by calculating it for this router on the left, which is almost always given in our book the letter U. So that's why you see U here. And then for all the remaining nodes, for all the remaining routers that are out there, if the router is adjacent to you, then you can calculate the cost directly. You know what the cost is. If it's a delay, for example, you can send a packet ping and get the response back and see how many total milliseconds that took. Now you know, cut it in half, and that's how long it took to get there. So if that's what you're going to base your cost on, now you have it. If you have routers on your network, but they're not directly connected to you, then you have no idea what the cost is. You have no idea that you can even reach them, really. You have no idea who to ask for help. So you're going to start off by marking these down as a cost of infinity. All right, so that's your initialization. Then you go through the loop, and every time you're going to see how much it costs to get to routers around you. And one of them will be the least cost, but I'm going to show you rather than tell you because it's way easier to figure it out this way. All right, so of course they have to change the diagram right off the bat. Like, it's very irritating. But we still have 6 routers and we still have 10 links. And we're going to start with U, and U is in black. So I'm going to change it to white so you actually have a prayer of seeing it. We're just fixing all kinds of problems here today. We're getting you your first job taken care of, some scholarship money, and we're cleaning up some slides. All right. They all changed, but this one. I must not have clicked on it correctly. Of course, it's not going to do me a lot of good because on the next slide and the next one and the next one, it's right back to the same freaking diagram again, right? So we'll save it out. All right. So here's our initialization. And I can see from you on the left. Get it? I can see from you. You can see X, you can see W, you can see V. So I'm going to mark down for W, X, and Z what the cost is. And the nomenclature that I'm basically going to use is I can reach V in a cost of 7 by sending the packet through the router U. That just happens to be me. So it sounds redundant, but this nomenclature, if we stick to this, it'll help us build out the rest of the table, and the answer will not always be U. Get it? All right. So I can reach X in 7. I can reach W in 3, and I can reach X in 5, and I can see that from right there. So let me fix another thing here. So maybe I can move this one to the back. All right, so at least it's a little bit more readable. It's kind of on top of my letters. Okay, I'll knock it off editing the slides during class, I promise. But I will, at least now I've got this thing fixed, I will copy it. All right, so we're done with step 1. I don't know how to get to Y or Z. I don't have any direct connection to them, so their cost is infinity. So I'm ready to make a conclusion already. I'm ready to make a decision about what have I learned from doing this? Well, I should convince myself that I now know, without a doubt, the least cost to get to W. There's lots of ways to get to W on this diagram from U, but they all start with a hop that costs more than the one that I already have. So one of the ways I have to get to W is to go directly to W. Another way I have to get to W is to go via X, because that's one of the other 2 routers that I connect to directly. But the cost of that is already higher than the one that I have. So it's impossible that I could go this way and get to W for less than what I already have, because it's already more expensive, and the same thing with V. So I'm done finding the least cost path to W. So I'm going to mark it off my list and add it to my list of N prime. Then I'm done, and not worry about calculating anything for it again. So while we're doing this, I'm going to place this diagram in. And I'm going to go to the next slide. So I've circled the 3U pair. And so what that's basically telling me is if anyone wants to get to W, and this is the routing table for the router on the left. This is the routing table for U. I now convince myself I know how to do it. So now I'm going to add W to my list, and I'm going to turn to W, and I'm going to ask W, who do you know how to get to? Maybe you know how to get to someplace for cheaper than I do. Do you know how to get to V? And W will say, well, as a matter of fact, I do know how to get to V. Well, what's your cost to get to, get to V? Well, it's right here, right? It's 3. All right, well, what was my cost to get to W? If you're going to screw this algorithm up, you're going to screw it up right here in the very next sentence I'm going to tell you. When you know the cost to get to a hop from the router that you are now examining, you have to remember to add the cost to get to it. You do not eyeball it on the diagram to figure that out. You look in your table. And your table told you that you made the conclusion a minute ago that the cost to get to W was 3. So if W knows how to get to V in 3, then you add this to it. And your cost is 6. Is it better than the 7 that you had before? Yes, it is. So I will write down, I now know how to get to V in 6 via W. What about getting to X? W also knows how to get to X. He can get to X in 4. I add 3 to that, not because it says 3 here, but because it says 3 in my table. Don't mess that up. And it's 7. It's not better than what I have. I stick with what I've got. What about, can W get to Y? W can get to Y in 8, plus 3 to get to W. So that's a total of 11. Is it better than what I had? Yeah, I had infinity before, so it's better. So I can get to Y in 11 via W. And I still can't get to Z. So we move on to the next diagram. Out of these that are left, I pick the one with the lowest cost. I should convince myself that I've now discovered the least cost path to get to X. Because even though there are other ways to get to X, they are going to start off with either a 6 or an 11. And those are the only other ways that are left that I know of, or an infinity. And therefore, this has got to be the best way to get there, the least cost. Nothing will be less than 5 because these numbers are already bigger than that. Okay, so I'm going to continue on with my table and Johnny Appleseeding my diagram as I go along as well. So I circled 5 and I add X, which was the one that had that cost, to my list of routers that I'm finished calculating, to which I'm finished calculating the least cost path. And now I turn to X, who's the new guy on my list, and I say, who do you know how to get to? Do you know how to get to V, for example? I don't ask him about W or X anymore because I'm done with them. But V is still in play. So I ask X, do you know how to get to V? Yes, in 7. Plus, what does it cost me to get to X? Do not eyeball it on the diagram. Look it up in your table. It costs you 5. That's not better than what I have, so I leave it alone. The same thing happens for Y. It's not better. However, X does know how to get to Z in 9. And I add to that my cost to get to X, which was 5. So I can reach Z in 14 via X. All right? So via X. Out of these 3, V is the least cost. I will circle V in red and add him to my list of finished routers. And I'm almost done. I only have 2 guys left. So I go to V and I ask V, who do you know how to get to? I don't need you to tell me how to get to yourself, W or X, because I'm done with those. I'm really only interested in what it costs you to get to Y and to Z. And this is actually a Y here. This isn't X. I mean, this isn't a V. Let me move him up so I can see him a little bit better here. Okay, and then of course I've got to go back and later replace the others. So here's V down here. Does V know how to get to Y? Yes, he does. He knows how to get there in 4. What does it cost me to get to V? It cost me 6 for a total of 10. That's better than what I have, so I'm going to replace my entry and say I know how to get to Y in 10 via V. And my path to Z doesn't change. Y, I'm now convinced it's the least cost path, so I'm going to circle him in red and add him to my list. The last one I have now is Z. So I go to Y, the last guy to come, and I ask him, do you know how to get to Z? And Y does. He can get there in 2. And what does it cost me to get to Y? 10 via V. So total of 12. That's better than what I had, and so therefore I can get to Z by going through Y at a cost of 12. And he's my last one. I circle him. I have just finished building this table using Dijkstra's algorithm for the router U. What I will give you as an assignment is continuing this diagram and building it for one of the other routers. It's the same exact process. The routing table will be different. What's really interesting is you end up with a shortest path tree out of this. And to give you a little more insight into that, I'm going to instead switch over to our website and show you an animation. So here is one of the exercises that we have, and this one has given me the following diagram. And what I'm going to try to do quickly is build a routing forwarding table using Dijkstra's algorithm for you guys. We're going to do it manually. Okay. I don't want to use those colors. I want to use this color. Okay, so I have N prime over here. Well, except I got to turn off the tool. I have M prime here. I'm going to start with U. The routers I've got to calculate it for V, W, X, Y, and Z. All right, so who do I know how to get to directly? I can get to V in cost of 1, myself. I can get to W in a cost of 2, myself. And I can get to X at a cost of 6, myself. I don't know how to get to Y directly, and I don't know how to get to Z. Agreed? Out of these three, the one that's the least cost is U. In the homework, if you are staring at results where two routers have the same least cost, like they're both 1. Let's say this one was 1 over here as well. Please choose to circle the one on the left in this table so that your answer will match the one that I calculate and the TA will not count points off for no good reason. I don't want to create 5 different versions of the solutions, and it's likely to happen. All right, so I'm convinced I know how to get to V, so I turn to V and I ask V, all right, V, who do you know how to get to? Can you get to W? Yes, he can get there in 5, plus the 1 that it cost me to get there. That's not any better than I had, so I stick with what I had before. Can you, Mr. V, can you get to X? Yes, I can get to X in 5, and it cost me 1, it cost me 6, thank you. It cost me 6 to get to U before, so that's not any better. Am I doing this right? I think I'm getting myself confused. I think I'm looking at the wrong router. Let me ask it again. I ask V, do you know how to get to X? Yes, I know how to get to X. I can get to X in 5. It cost me 1 to get to V, so says the table. Total of 6. It's the same as I had before, so you could switch if you want, but you might as well leave it alone. V, can you get to Y or Z? No. Can't get to either one. All right, so I'm going to circle what I have here. U, V, and W. It's kind of nice that they're going left to right here. And I turn to W and I ask W, do you know how to get to X? He knows how to get there in 5, and it costs me 2 to get to W, so that's a total of 7. No better. Do you know how to get to Y? Yes, 9. And it costs me 2 to get to U. I can get there via W. What about Z? Yeah, same thing. I can get there in 9 via W. Out of these, X is the best one left. U, V, W, and X. I ask X, do you know how to get to Y? No, I don't, so I leave this alone. Do you know how to get to Z? No, I don't, so I leave this alone. Out of these, this one is the least cost. And so I go U, V, W, X, and Z. And I ask Z, do you know how to get to Y? Yes, I do, in 6. How much does it cost me to get to U? 9. That's a total of 15. It's not any better than what I had before. I'm going to keep what I had. I'm done. All right? And hopefully I didn't mess it up. All right, here's one of the fundamental failings of destination-based routing. I have 10 links on this diagram. You're paying for these links. I mean, somebody paid for them. You know, even if they're on your own campus, you had to pay a crew to come and dig the dirt and run the cable and pay for the wire that you put in there. So how am I doing using this thing? Well, I have U, and I have a route to V, says so right here. And U also has a route to W. So I'll use his own direct route there. And I also have a direct route to X. And I go through W to get to Y. And I go through W to get to Z. So if I color this in my diagram, out of the 10 routes I purchased, I'm using this one, and this one, this one, and this one. And I'm not using the other 5, ever. So you can have a situation, which happens all the time, where you have a router with 3 ways to get to a destination. And each of these 3 routers have a 50 megabit per second link. 50 there, 50 here, and 50 here. And you show up with 100 megabits per second to send. Can you get it there? Well, you and I would say yes. The internet cannot, because it's going to pick one route and use it exclusively. And you will never get the benefit of the other ones. So there's no traffic shaping in pure destination-based forwarding. So you either have to hack your router or switch to something else like software-defined networking. And what software-defined networking might say is, what time is it? No, I mean like down to the 10,000th of a second. If it's an even number, route it on the top one. If it's an odd number, route it on the bottom one. So back and forth you go. Every 10,000th, even odd numbers. You might say if it's coming from this network, then, or this collection of IP addresses, send it over the top one. And if it's coming from this collection of IP addresses, send it over the bottom one. And if you see that it's lopsided, then just push some flows down that groom it, that shape it. This is called traffic shaping, and we cannot do it on the internet the way we have it right now. All right, what we didn't have time to cover today, which we had to, so we're going to have a problem here. We're going to have to go fast next time, is Hamming code. Hamming code is a technique to protect data in transit, but it's not super critical for us. It's more of a computer architecture thing. So I'm okay. In fact, I may change my mind and boot it. I may decide we don't need it, because I usually do force everybody through it in architecture, and most all of you have taken architecture from me before or will have to take it soon. If you're a comp sci major, you don't have a choice, but there are other majors in our classes there as well. But at any rate, I'll just at least flash that for you. So this, like all the other ones, will show and hide the solutions. It'll show you what it is here. 1, 2, 6, 11, 9. This is where you find out if I know what I'm talking about. 1, 2, 6, 11, 9. Yay. Okay, good. Got the same one. And they'll show you the least cost links. He didn't draw a tree, but he at least did match me here. W to Z, W to Y. Everything else is directly from you. Yeah, that's what I got too. Okay. Hopefully this is new stuff for you. Hopefully it's interesting for you guys. Thanks for toughing the cold to come to class. And thanks for the rest of you for taking advantage of it online. And I'll see you guys on Thursday morning online. Bye, everybody.